Hello and welcome to the first video in the Year 10 radioactivity topic. Today we're going to be looking at the Plum pudding model and Ernest Rutherford's experiment to verify this model. In the early 20th century, physicists were investigating the structure of the atom. They already knew about the electron, which was called the negative corpuscle, and they were investigating how this negative particle could be incorporated into what they knew must be a neutral atom. J.J. Thomson came up with one of the first models of the atom, called the Plum pudding model. In this model, he took the electrons, or the negative corpuscles, and had them dotted throughout this spherical cloud of positive charge. He postulated that the total negative charge of the electrons must exactly equal the total positive charge from the cloud, enabling the atom to remain neutral overall. This model was referred to as the Plum pudding model, as it reminded scientists of the time of a common pudding where you would have the sponge with the fruit dotted throughout. Nowadays, we could imagine this as a blueberry muffin. J.J. Thomson's model of the atom was published in March 1904. Soon after that, Ernest Rutherford, another prominent physicist of the time, set about designing an experiment to verify this model. The diagram here shows the experimental setup for Rutherford's experiment. It was conducted by his two students, Geiger and Marsden, and is sometimes known as Geiger and Marsden's experiment. So, looking at the apparatus, we'll see it starts off here with a narrow beam of alpha particles, which are fired towards a fine gold foil. These alpha particles had recently been discovered by Rutherford, and he had classified them in 1898. Whilst he didn't know the structure of this alpha particle, he did know its charge and its mass. Following work completed later after this experiment, we now know that the alpha particle is made up of 2 protons and 2 neutrons, just like the nucleus of a helium atom. Surrounding this fine gold foil was a zinc sulfide screen. As the alpha particles collided with the zinc sulfide screen, they would emit a tiny flash of light called a scintillation. Geiger and Marsden would then count these scintillations of light by eye and record them for every single angle around this screen. This was a painstakingly long process which took years for his students to complete. Rutherford then went on to analyse these trajectories of the alpha particles to enable him to investigate the structure of the atom. There are a few key elements on this diagram which we are yet to discuss, but which play pivotal roles in allowing this experiment to provide accurate results. We'll discuss these now. Firstly, you'll notice that this whole experiment is conducted within an evacuated strong container. This meant that a vacuum is created inside this circular ring here, which means there are no air particles to interact with the alpha particles. It was known at this time that alpha particles could only travel up to a few centimetres in air before being absorbed, and therefore without this vacuum the alpha particles would never be able to reach the fine gold foil, let alone be detected following their interactions. You'll also notice that this alpha source was contained within a long metal box. This metal box around the outside here was made of lead, and lead was a very good absorber of alpha particles. You'll notice on one end though there's a small gap allowing the alpha particles to exit. This meant that Rutherford knew the exact trajectories of the alpha particles before they reached the fine gold foil, enabling him to track their paths much more accurately. If this was not the case, then an alpha particle could theoretically leave the alpha source along this trajectory, then be detected by the zinc sulfide screen, and Rutherford would have no way of knowing whether that particle had interacted with the fine gold foil or not. Lastly, it's important to notice that the gold foil is very thin. Gold was particularly selected for this purpose as it is able to be beaten into a very thin sheet, almost invisible to the human eye. This means that the alpha particles are less likely to be absorbed by the gold foil, but instead they can be detected by the zinc sulfide screen, allowing Rutherford to collect all of his data. So, we've now looked at J.J. Thomson's plum pudding model and the design of Rutherford's experiment to verify this model. The question I leave you with is this. If the plum pudding model were to be true, what would Rutherford have expected to see within his results? For example, which angles would he expect the alpha particles to have left the gold foil at? We'll discuss this in next lesson.